So we'll start the session with Kaline Coutinho. She'll tell us about solvent effects on the electronic properties of mononuclear aqua catalysts for water splitting. Thank you.
Okay. So, good morning, and thank you, the organization, for the invitation. I will talk about theoretical modeling of molecules, looking to properties of catalysis that goes in the water splitting reaction. This project was the project of my student, Leandro. His PhD finished last year. And I'm from the University of São Paulo, and this is my email. Who wants to talk to me or send message? And I thank all the support funding agencies. Okay, this work that I'm going to talk about, we are going to talk about the X-ray photospectroscopy fingerprint of intermediate processes of this catalyst that made water splitting. And why study water splitting? The idea is that we are going in the direction of the green chemistry, that we want to split water to generate gas, O2 and H2. And with these two gas combusting, we are going to generate water as the garbage of the combustion, okay? So then we have a clean combustion. Okay, the idea is that we have several metals atoms here where we can coordinate with organic parts. And with this metal, we are going to do a reaction where we are going to take protons and electrons. And this metal will complex with water and form this kind of complex with a hydroxyl. And then this complex with the double bond with the oxygen. And then in the literature, we know two different proposals of chemical reaction where we can have the generation of O2, look into a mechanism where you have a direct interaction of water in this oxygen here. Or you have this complex and they make a dimer, and then they form the O2 again and come back to this one. So the idea is to study how this reaction occurs and modifying the pH and also the oxidation compound in the solution, you can generate the intermediate. And the point here was the question, look into the X-ray photospectroscopy. This is a very powerful technique where you can insert a radiation with a specific energy that is atom-specific, in the sense that you can remove the electron from the core orbitals, okay? So in this sense, you can select a specific atom to remove the electron, and then you can see the surroundings of this atom and also the charge of the atoms. So then, if we use this technique, the idea was, can we see all the oxidations of the ruthenium, was the metal atom that we wanted to study? Here is ruthenium 2, ruthenium 3, ruthenium 3, ruthenium 4. And also, you are connected with hydroxyl, water, hydroxyl, and only the oxygen, and see if we are able to look and see all the fingerprint of these different charged ruthenium with different coupling interaction with water, okay? So the system that we are going to study is one system that ruthenium coordinates with water, but also has one coordination with pyridine and two bipyridines. In this sense, I put here the electronic, the illustration of the electronic part of ruthenium. And as you can see here in the last orbital, if we take off 2 electrons, we are going to have 6 bonding, okay, 6 coordination. And we have 1 bipyridine where the 2 nitrogen interact with the ruthenium, the other bipyridine that the 2 nitrogens also interact with the ruthenium, and 1 pyridine. So you have 5 nitrogens, and the last coordination will, are going to happen with the water solution, okay? Because all these complexes will be put in water. So then we started with ruthenium 2 interacting with water and have charge 2+. Then when we take one proton away here, we are going to have ruthenium and also taking 1 electron. We have ruthenium 3 and also a hydroxyl, the total charge is 2. So we have 5 different species where we are changing the total charge of the complex, but also the oxidation of the ruthenium and also the complex that is connecting with the ruthenium. And looking to these 5 different complexes, we are going to follow the reaction that generate this metal with the bond, double bond with the oxygen, okay? It start interacting with water and then finish interacting only with the oxygen without the 2 hydrogens. And to make it simpler, I put different colors, red, black, green, orange, and blue. Each one, I'm going to take all this color for the rest of the presentation. Then you can visualize that each color represents a different species, okay? So when we started when we started the collaboration, the idea was the chemistry, they prepare different systems, solutions with different pHs, so they knew how the form of water is interacting with the ruthenium, and also different concentration of oxidant, that they know the oxidation of the ruthenium, okay? And look into the XPS spectrum with different chemical properties, we can see the peak that is characteristic from the ruthenium, is this region here, okay? And when they look, they see that for this first peak here, we have the ruthenium at oxidation 2 and bonded with hydroxyl, charges +1. So this is the first binding energy, okay, is in 285.7 AV. Then the next one is in the same position, these 2, ruthenium with charge, total complex charge 2 here above, but the ruthenium with oxidation 2 and 3 on this energy. Then the next one comes this green peak here, that we have the ruthenium with oxidation 3, the total charge 3, and this, and the last one, the blue one, okay? So we are looking to this, orange, red, black, red, this red here and blue here, okay? So the idea that we have this order, orange, red, black, green, and blue. And the difference in energy between all these peaks is around 2.5 eV. And then all the molecular modeling were performed in general for the most people that study this kind of oxidation and complexes, large in this size. They calculate this molecule in vacuum or in continuum model solution, okay? So it means that the complete water solution is going to be described in the quantum mechanical calculation as a dielectric constant, but not explicit water molecules. And when we perform this kind of calculation, you can see that we start with the binding energy in the orange here, but then we have red, black, and then we have here the different position of these 2 peaks. Okay, we have in the theoretical calculation the blue and the green, and the idea was that in the theoretical calculation the difference between the peaks were 5 eV. So 5 eV from 2.5 is a very large error, theoretical error. And additionally, as you can see, we have here the distribution of the peak following the total charge of complex, +1, +2, +3. Okay? So, but the experimental data does not show this kind of behavior. So the idea was, as we are committing a large error in the theoretical description, we should improve the interaction with water. So then we start to do that. For do that, we use a hybrid method in a sequential way, where we are going to use quantum mechanical calculation to calculate the binding energy of the electron in the core orbital, and also molecular mechanics to generate the structure of the complex surrounded by the solvent, okay? So in the first part, we use classical molecular dynamics, either with Monte Carlo simulation or molecular dynamic simulation. We generate structures. We analyze the statistical correlation between these structures. We select a structure that has new information, and then we test how long the size, how many water we should include to describe properly the experimental data, okay? So doing that, we are going to select some clusters, in general around 100 clusters, and perform ab initio calculation to calculate the binding energy. This is the idea. So doing that, the first point was that when you perform a classical molecular dynamics, you are going to have several parameters to describe the interaction between the solute and the solvent. And in general, all these charges are calculated. In general, the potential describes a van der Waals part and also a Coulombic interaction between the two different molecules. So to have the Coulombic interaction, we need to calculate the atomic charge distribution over the atoms. And in general, this calculation is performed in vacuum. When we do that, we are losing the polarization information. So to do that, we use a methodology that we developed that is the interaction, the iterative sequential QMMM. We start with the charges of vacuum. Then we perform the simulation. After that, we have the distribution of the solvent around the solute. And then we use all this structure to recalculate the charges over the solute. With these new charges, we start again the simulation, generate new structures, and then calculate new charges. So we do that until we have converged charges to equilibrate the interaction between the solute and the solvent. And then we call these charges as polarized charges. Okay? Doing that, as I'm telling here the summary of our procedure. First, we performed the vacuum calculations with the clusters, with the ruthenium, bipyridines, pyridines, and water. Then we stretch this water molecule away and closer to calculate the quantum mechanical potential, is the black one. And we use the classical parameters of the molecules to analyze and see if you are well described the interaction between the ruthenium and the water. And then we need to generate new parameters to best describe the interaction, mimic the quantum mechanic interaction, okay? So we do not use the common parameters to describe the interaction, but we first performed quantum mechanical calculations, generate the energy profiles between the complex and the water, and then we generate new parameters to well describe this interaction, okay? So our parameter is this red one here, very close to the black one. This is the quantum, and these other parameters are ruthenium parameters that we find in the literature. Make it for other complexes, okay? So the ruthenium is very sensitive to the coordination molecules. After that, we performed the simulation. we analyze the statistics, generate the clusters, and with these clusters that include the solute and the first solvation shell of water, we calculate the absorption spectrum, the binding core energy that we are going to compare with XPS spectra, and also we can study the reaction of the protonation and oxidation of the ruthenium. So, doing that, what we can see is when we are changing from one complex to the other, this is the distance between the oxygen and ruthenium. This is in red. See, the first complex, we lose only one electron, and then water becomes closer. Then we lost one proton and one electron, more closer, and so on, until going to this complex here. So we can see that the process of lose hydrogen and electron is making a stronger interaction between the oxygen and the ruthenium. Also, we are showing here the distance of all other 5 nitrogen. And you can see here that most of the nitrogen, they do not feel this change when the water is losing proton and the ruthenium losing electron. But the trans nitrogens feel that. So this is the very known effect that the most sensitive coordination was the opposite of the point where the reactions take place, is this nitrogen 11 that you can see here the distance. So with this analysis, we can show that in fact we have the trans effect that is well known by this kind of process, okay? So additionally, what we can see is that when we look to the charges of the groups, I put here in red the charges of the water group, in black the charges of the ruthenium, and in blue the charges of the nitrogen. And now over I put the charge calculated in vacuum, and in the down part I put the charges with the polarization in water. And as you can see, for some complexes, we don't have a large difference on charges. But if you look this kind of complex, you can see that you have a bigger difference between the charges calculated in vacuum and charges calculated in solution. And the idea is that if we think that the binding energy of the ruthenium electron in the core orbital depends only of the electronic distribution of the ruthenium, you can look to this kind of charges and see the sequences. So this is the experimental sequence here, and you see if we look to the gas phase charges, the sequence is completely different from the experimental one. Okay? When we go to the in-solution charges, so we have some much closer sequences of the binding energy, but we have an inversion here between these two complexes. Okay? And this complex with the charges 2+ and oxidation of the ruthenium, oxidation 4, is much difficult to describe. Okay? So, thinking that we can see that for this kind of system, the polarization is important, and the effect of all waters change the charge density of the ruthenium. Okay? But we do not correlate this change with the experimental data, so something is missing. Then we use these structures, also generated from the simulations, to calculate the absorption spectrum of the ruthenium, to see the energy of the electron in the valence, not in the core, but in the valence orbitals, okay? So doing this kind of calculation, here I'm showing you only the result obtained for the single complex in vacuum. This vertical line are the excitation energy that we can calculate it, absorbing the electron and excitating. So when we performed now the ruthenium with a continuum model, as you can see, you have the same vertical bars, but with a small displacement. But when we start to put here the complexes with all the other waters described as punctual charges or the electrostatic environment of the system, and also 100 different configurations, we started to see a better description of this peak here. And also, when we include explicitly the hydrogen bonds and the complex in the quantum calculation and the solvent as an electrostatic environment, point charges, we can see an even better description of this blue line is the experimental data. So we consider that our modeling is very good because we can describe in very good description the absorption spectrum. So for the literature standard, this is the very, very, very good comparison between theoretical calculation and experimental data, meaning that our simulation, our parameters, our density of charges are well described. Okay, so, okay, now to finish, what we wanted to see is that what happens now when we put the calculation with the solute and all the first solvation cell. It means 70 water molecule in the quantum calculation to calculate this core electron binding. So as we can see here, I put here the order, orange, red, black, blue, and green. And this is the calculation of vacuum. But now this is the calculation when we put the entire solvation shell. As you can see now, we have the orange, red, black together. We have a small displacement on the green and the blue. And if you look to that and look to the experimental data, we have now the same behavior as the experimental data. And also, when we look to the data, the displacement of the bands, this is the experimental displacement if we put the 0 on the red, okay? And now we have the theoretical calculations showing that we have the same order of magnitude of the displacement. So what we conclude from that? We conclude that even if we are looking to a property that is very local from an atom, like the core energy to take the electron from the 3D orbital, this property is sensible to the entire solvation shell of water. If we put only the 2 hydrogen bonds that form, we don't have this result. If we put the entire water molecules as continuum model, we don't have this result. Only when we include the entire solvation shell. So it's very interesting that a very core property can be changed by the entire solvation shell. And this shows that for many problems, mostly reactions, we need to consider the entire environment to see the correct experimental trend, okay? So with this, I finish my presentation telling that we use this sequential QMMM method using DFT for quantum calculation and Monte Carlo and molecular dynamics for the simulations. And also, we calculate several electronic properties, the valence excitations and the core excitation also. For the XPS, we were able to describe and to assign the peaks as the experimental expected, considering the polarization of the solute and the explicit inclusion of the all first solvation shell, and all the polarization and the first solution are very important. So I finished my presentation, leaving here my contact, and thank you for your attention.
Okay, we're open for questions.
Kaline, very, very interesting. So regarding to the water splitting, which one of those configurations may favor in terms of catalysis? I know that, I mean, here you bring the, from the methodology point of view, but experimentally it will be interesting in as well for the theoretical point of view to identify which of these species as an atomic catalyst
Yes.
may favor. If you can take some information from what you have.
Yes. What we can understand from here is that the idea that you have a metal atom is very interesting because the metal atom is very reactive. So if we have the experimental information, look into a series of different, the same atom or a different metal atom and different ligands. And if we can perform a quantum mechanical calculation, include the solvation shell, we can understand better why this metal or why this ligand are doing this effect. So what we showed here is that it's not enough to use the current methodology with continuum model. We need to go beyond and use explicit water. But if the experimentalist has a series, for example, 5 or 7 different compounds that they tested, and then now look into the electronic properties, you can understand, okay, this catalyze is better, but I'm seeing this kind of flux of electron or this kind of binding energy moving on, or the steric effect leaving a space to the water coming and interacting. So I think that we showed that in the literature, most of the people use the simplest model, that is the continuum. And this is not enough. But now, if you have a real series that was tested by the experimentalist telling us the percentage of water splitting coefficient, we can now make correlations between electronic properties and experimental and predict or tell the experimentalist, so you should change one group here to put more electrons or take off more electrons. So this is only the starting point to show that this methodology with explicit water describe much better the system compared with the continuum one. But we did not see a series, because for each metal and each series of ligand, you are going to have a different effect.
Very nice, Kaline. Very nice aggregation of several different methodologies, very complex, by the way. So this effect of water, I wanted to understand where it comes from. So is it like the effect of a dielectric medium?
No.
Or it's the change in the geometry or something like that? So
Yeah.
how do you understand this effect?
If it was the dielectric medium, this continuum model will answer correctly. So as the continuum model doesn't answer, it's not the dielectric, okay? First. The second one, the geometry. We look, all these simulations were performed with the entire flexible system, we can see. But as we have the 2 bipyridines and the pyridine, the system is very rigid. You can see a small rotation of the pyridine and a small rotation of the water molecule, depending on how many protons they have, okay? But is not very dependent on their geometry. But if you consider that when you change the complex, optimizing the geometry, you are going to have almost the same behavior as have the flexible one. So what we think is that when you have the orbitals, you have a delocalization between the complex and the water. And the water is binding to the other waters. And all these other waters, they are going to distort the orbitals, making a slightly different electronic distribution. How I try to show when we put the polarization charges. But the point here is that we are calculating these polarization charges considering all the water molecules as point charges. But if we try to calculate with explicit water with orbitals, these calculations take really long times. So the point is that this polarization is very important, and as much water you take into account, we are going to have a better description of this polarization that change the electronic density and change the electron affinity.
Cool. Any other questions? Then if not, let's thank Kaline again.
Okay, thank you.